All right, we're starting to get in circular motion now. What I want to look at here is what's called the conical pendulum. And we do a practical in 3.1 with this, and it's where you you hold an object on the length of a string, and instead of just going backwards and forwards, it goes in circles. So if we draw this, we've got the length of string, and we've got the object on the end. And it sort of goes round and round in circles. So it's not just swinging backwards and forwards. We will be looking at the pendulum when we do simple harmonic motion, but that's not what we're doing now. So the thing to remember with the conical pendulum, we've got the circular motion. So with circular motion, you always need a centripetal force. So Fc from year 12 equals mv squared over r. So that's the force you need to make this object go in a circle, the mass being the mass on the end of the object. So where's that force going to come from with the conical pendulum? Well, we've got only two forces acting on this pendulum, mg, which is the weight force, and we've got a tension force, Ft, in the string. Now those are the only two forces. So if we draw a force diagram, those are the only two forces we can actually draw, apart from a net force. So if we draw the diagram over here, mg, this is the force diagram now. So I can now draw these vectors adding up. These two vectors are acting at the same point, the center of that center of mass. So that's mg. We know that the tension force has to go in the same direction as the string, and we know the centripetal force is horizontal. So our vector diagram is going to look like this. We've got Ft and we've got mg, and then we have a net force like that, F net. Now that net force is the only force that's really operating. It's like the sum, well it is the sum of these two vectors. So that net force, F net, must be equal to Fc. That's the force that makes it go in a circle. So F net equals mv squared over r. So remember, the only two vectors that are really there are mg and ft, but if we add them together we get F net, which is equal to Fc. So that's pretty good. We've made some good progress in understanding it. Now, what about angles? This angle between the vertical and the string we'll call theta. So that's the vertical, that's the angle of string, so that also is called theta. Now we can work out a few things here. We could say Ft times the cos of theta is going to be equal to mg. Right? We can say that. We can say Ft sine theta is going to be equal to F net, which we've already said is centripetal force. Starting to get some information here, right? So let's solve for Ft, if you like, because we've got two Ft's there. We can say Ft cos theta equals mg. So Ft equals mg over cos theta, right? That would be nice and easy enough to do. But we want to do something a little bit more, even a bit more interesting. We could have the Ft cos theta equals that, Ft sine theta equals that. So let's just do that. We've already written that down. So we've got that there. So mg cos theta over sine theta. Well, let's just write this down. So Ft equals mg over cos theta, and this Ft, which is the same one, equals mv squared over r, right? And let's bring down the sine theta. Now we'll move to another little bit of paper here. So we can say that mg cos over cos theta is equal to mv squared over r sine theta, right? Looking nice. We just equated the two Ft's. Now, if we bring the sine theta up here, so we can actually say, put the sine theta up there, and go mg sine theta equals mv squared over r, right? So we've got the sine theta up there, mg sine theta, we've still got the r there, mv squared over that. We've still got the cos theta over here. Let's bring the mg down. So we can bring the mg down. And what we've got is tan theta, right? Sine theta over cos theta equals tan theta. So we're making progress here. We can cancel those m's. And we've got rg. Let's bring that rg back up. Gets rid of the rg. Equals v squared. So we can say v equals the square root of rg tan theta. Something worth remembering, that one, because it's going to come up a couple of times. So this is the conical pendulum, and what's that formula telling us? It's telling us that the velocity that that pendulum swings at, and whenever you get a formula in physics, you should have a look at it and say, what does that mean? And what we're basically saying is that that velocity is dependent on r and g and the angle. All right? Its gravity doesn't change, so it's more dependent on the radius and the angle. It's got nothing to do with the mass. If you increase the angle, and if we know our tan graph was 0 to 90 degrees, it goes like that. That's our tan graph. If you increase the angle, the tan goes up. So if you increase the angle, the speed must go up. If you increase the radius, the speed must go up. Okay, to the square root of the increase. So that's our little formula for the conical pendulum.